Implication. The implication elimination rule is very easy. We assume that S is an assignment that satisfies in M the assumptions B1 to Bm, B1 to Bn, and we assume S satisfies in M A implies B, and S satisfies in M A. We show that then S satisfies in M B, but this is trivial. We can consider two cases. If S does not satisfy A, then the implication introduction rule. Implication introduction rule. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn. By induction hypothesis, we may assume that the short derivation of B from A, the temporary assumption A, is sound. That is, if S prime is any assignment that satisfies in M the assumptions B1 to Bn, and moreover S prime satisfies A, then S prime satisfies B, whatever S prime is. Now we prove that this S that we have satisfies A implies B. Case 1. S does not satisfy A. Well, then it certainly satisfies A implies B. The other case, S satisfies A. Now we apply the assumption. Now we apply the induction hypothesis. And we get that in this case S satisfies B in M. So anyway, S satisfies A implies B. Equivalence, we leave it as an exercise. Negation. This is again more interesting. We assume that S is an assignment that satisfies in M the assumptions B1 to Bn. By induction hypothesis, we assume that the inference of B and not B from A is sound. That is, if S prime is any assignment that satisfies in M the assumptions B1 to Bn, and moreover S prime satisfies A, then S prime satisfies B and not B. But S prime can never satisfy B and not B. So in particular, S cannot satisfy A. Otherwise S would satisfy B and not B, which is impossible. Hence, by the truth definition of negation, S satisfies negation A. Note that this does not mean that S does not satisfy A, whatever S is, only that S does not satisfy A for those S that satisfy the original assumptions B1 to Bn in M. Negation elimination rule. This is easy. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn, and moreover let's assume S satisfies not A. We show that S satisfies A. but this is clear. Quantifiers. First we have the universal elimination rule. From a formula for all xa, we deduce a with a term t substituted to x. And of course we assume that t is free for x in a. Now, suppose S is an assignment that satisfies in M the assumptions B1 to Bn, and S satisfies in M for all xa. Then for any A in M, S A/X satisfies A in M, in particular if A is a value of the term T in M under the assignment S. By the substitution lemma, then S itself satisfies in M A T/X. This was the universal quantifier elimination rule. Then the universal quantifier introduction rule. From A we deduce for all xa, but of course we have to assume that the variable x does not occur free in any uneliminated assumption of the deduction of A. So suppose S is an assignment that satisfies in M the assumptions B1 to Bn. Suppose also that S satisfies in M all uneliminated temporary assumptions in the deduction of A. Note that this little application of the universal quantifier introduction may be part of a big deduction in which some temporary assumptions have been introduced, and their temporary nature has nothing to do with this particular step. For example, there may be outside this application of the universal quantifier introduction rule a grand scheme to use implication introduction rule, and as you hopefully remember, the implication introduction rule puts the hypothesis of the implication as a temporary assumption and tries to prove the conclusion. Such temporary assumptions may occur in this deduction. So, we assume that S satisfies in M all uneliminated temporary assumptions for the deduction of A. Now, for all A in M, the modified assignment SA/X also satisfies those assumptions since X is not free in them. So, the change of the value of X from whatever it was to A when we pass from S to SA/X does not have any effect. This needs a simple proof, but we omitted. See problem 211. Okay, now we can use the induction hypothesis and apply it to the assignment SA/X and conclude that SA/X satisfies A. And since A was arbitrary, S satisfies for all xa. So there was a little complication in this part of the proof in handling the temporary assumptions and the induction hypothesis. In fact, the way the induction hypothesis is used is kind of subtle. Now the soundness of the extensile quantifier elimination rule. The variable x should not occur free neither in B nor in any uneliminated assumption in the deduction of B, except perhaps in A. And of course, in a typical application, A does contain x free. Suppose S is an assignment that satisfies in M the assumptions B1 to Bn. Suppose S satisfies there exists xa and the uneliminated temporary assumptions used in the derivation of B from A. Again, let us keep in mind that indeed there can be such temporary assumptions which are different from B1 to Bn and which arise from the overall structure of the big deduction of which this particular step is part. So there may be a kind of grand scheme to use for example, disjunction elimination rule, and that rule introduces temporary assumptions which now occur in the derivation of b. And then outside this little step, they will be eventually eliminated. Okay, so we suppose S satisfies all the uneliminated temporary assumptions used in the derivation of b from A. We argue that S must satisfy b. There is a little a such that S little a slash x satisfies capital A. Hence, S little a slash x satisfies. There is a lowercase a such that S lowercase a slash x satisfies uppercase A. Hence, S a slash x satisfies all the assumptions used in the derivation of b from A. We use again problem 211. By the induction hypothesis, S a slash x satisfies b. Remember that x is not free in b, so since S a slash x satisfies b, also S does. Again, here we use the very useful fact that satisfaction depends only on the variables which occur free in the formula in question. Then the extensor quantifier introduction rule. This is easier. The term t has to be free for x in A. Suppose S is an assignment that satisfies in M the assumptions b1 to bn. If in this situation S satisfies also A t slash x in M, then by the substitution lemma, S a slash x satisfies in M A for lowercase a equal to the value of the term t in M under the assignment S. In particular, S satisfies there exists xa in M. If S satisfies a t slash x in M, then by the substitution lemma for the choice lowercase a equals the value of t in M under the assignment S, we have S a slash x satisfies in M the formula A. In particular, S satisfies there exists xa in M. Let us now formulate Soundness theorem, the result that we have proved. It says, if a formula of predicate logic has a natural deduction, then it is valid. Or more exactly, if a formula A of predicate logic has a natural deduction from assumptions which are satisfied by an assignment S in a structure M, then S satisfies A in M. Applications. We can show that the formula B is not derivable by natural deduction from a formula A by finding an assignment S and a structure M such that S satisfies A in M, but S does not satisfy B in M. For example, to show that there exists y for all x r0 xy is not derivable from for all x there exists y r0 xy. We can let the universe of the structure be the set of natural numbers 0, 1, 2, and so on, and the interpretation of the binary predicate R0 be the natural order of the natural numbers. Then any assignment satisfies for all x there exists y r0 xy, but it's not true that M satisfies there exists y for all x r0 xy.